Welcome everybody to our video series on probability and statistics. Once again, I am Dr. Lathram. So let's get started with our presentation today on CDFs, PDFs, and random variables. So let's begin by reviewing some of our definitions from probability theory. So remember, our starting point for our discussion of probability theory is with the idea of an experiment. An experiment is really nothing more than a process by which we make some observation. Now, for an experiment, we'll talk about something called a sample space. So the sample space associated with an experiment is the set of all possible outcomes for the experiment. So that's not just if we ran the experiment, here's the values that we get. This is more of a theoretical construction. This is if we ran the experiment an infinite number of times and every single possibility that could happen, that is what we are including in our sample space. By an event in an experiment, we say that that will be an element of something called an algebra of sets that we form from our sample space. So let's begin by reviewing some of our notions from probability theory. Remember that where we started with probability was with the notion of an experiment. Now, by an experiment, what we mean is that it's nothing more than a process by which we make some kind of observation. And so typically what we talk about in context of these events is something called the sample space. So the sample space associated with an event is the set consisting of all possible outcomes. So no matter how remote that possibility is, it's still a possible outcome, and so we're going to include it in our sample space. Now, by an event in an experiment, it's going to be an element of something called an algebra of sets formed from our sample space. Alright, so we just said that our probabilities are defined on this algebra of sets that we derive from our sample space. So what do we really mean by an algebra of sets? So if we have a sample space S, an algebra of sets is going to be a collection, script f, of subsets of S such that, first of all, the empty set is going to be an element of this collection. Second, if A and B are elements in this collection, then A union B is also an element of this collection. Now, kind of in common terminology, what we're really saying is if it's possible for A to happen in an experiment and it's possible for B to happen in an experiment, then it's entirely possible for A or B to happen in the experiment. So that's just kind of something that's reasonable to say. And finally, if A is an element of this collection, then the complement of A is also going to be an element in the collection. Now also, that kind of makes sense in our terminology of an experiment, that if it's possible for an event to happen, so when we say that A is going to be an element of script f, we're saying that it's possible for this particular event to happen in the experiment, well then it should also be possible for the event not to have happened in the experiment. And so that's just kind of a perfectly reasonable thing to say about this particular experiment, about any experiment for that matter. When we have a discrete, or we've got a countable sample space, countably infinite sample space, then the algebra that we will take will always be the power set of the sample space, so the set of all possible subsets. Now, when we have a continuous probability distribution, then our events will be open and closed intervals, and so formally the algebra that we're going to be talking about is something called the algebra of Borel sets. That may be a little bit beyond our notion of that we'll have in probability and statistics. To kind of save that for a next class on probably analysis or advanced calculus. But it's not bad to kind of be introduced to those ideas a little bit before you get there. Alright, so let's review our axioms for probability. So we had a sample space, we've got an event in this experiment that has a sample space S, so the probability of the event. Some things that we want to hold is that the probability of an event will always be between 0 and 1 inclusive. Our probability of the entire sample space will always be 1. And if A and B are mutually exclusive events, so that is to say if A and B cannot happen simultaneously, so the intersection of A and B is empty, then the probability that A happens or the probability that B happens is going to be equal to the probability of A plus the probability of B. Alright, so let's talk about what we mean now by a random variable. So we've kind of seen this in some of our previous videos when we do experiments like rolling a couple of pair of dice. Then we had an example of a random variable talking about the sum of the spots on the dice. So now let's be a little more formal, a little more concrete when we talk about what is a random variable. So a random variable y is really going to be a real valued function on our sample space taking values in the real numbers. So we say that this random variable y is going to be a discrete random variable if the image is either finite or countably infinite. So just to remind you what the image, so the image y of capital S is going to be the set of all the outputs that we get for every element of S. So a random variable y is said to be continuous if it is not discrete. That kind of makes sense. It's one of the kind of standard things in mathematics. That if y is going to be an element of the real numbers, then some notation that we have, we say that y is equal to y, so capital Y is equal to lowercase y, is really standing in to talk about the preimage of the element y, little y. So what's the preimage? Well, that's all of the elements in our sample space that capital Y, the function capital Y, sends to little y. If we want to be a little bit more general about that, if we've got a subset of our sample space, then the notation capital Y is equal to A really means that we're talking about the preimage under capital Y of the entire set A. And so what is that? Well, that's going to be all the elements in our sample space that land in A when we apply the function capital Y to the value. So now let's talk about the cumulative distribution function for a random variable. So if capital Y is a random variable, then if we choose some element of the real numbers, then the probability that capital Y is equal to little y is going to be the probability of the preimage of little y under capital Y. So remember what this is. This is going to end up being some subset of our sample space. So our functions y, as long as this is defined in our algebra of sets, then this probability makes sense in that case. Okay, for a discrete random variable, this is always going to be defined. Probably should make a stipulation that in the continuous case, that this function will be something called a measurable function. So that the preimage ends up being an element of our algebra of sets. That's kind of a fine point. We'll kind of mention it, but we really won't worry about conditions in which that's not going to be the case for us. It will never happen. All of our functions are going to be continuous functions. We've got the Borel sets, so that won't ever be a problem. And so for those kind of finer points, we'll worry about that for a later class on probability. But for now, just remember that our pre-images are going to be subsets of the sample space that we can take the probability of. So for a cumulative probability function, the cumulative distribution function, is going to be this function capital F of little y, which is going to be the probability that capital Y is less than or equal to little y. So remember what this is. This is actually the pre-image of an interval of from negative infinity all the way up to y, including y. So we're taking the pre-image of a set. And so this is again going to be a subset of our sample space. We're assuming that everything is defined. So our function is going to be a measurable function. So something that we can take the probability of. And so again, we're defining our probability as being on a subset of our sample space. So now let's define the probability density function for a continuous distribution. So for a real value random variable x, the cumulative distribution function, so the CDF, is defined to be this function. So it's the probability that capital X is less than or equal to some little value of x. Now that we say this CDF, so this cumulative distribution function, has a probability density function, has a PDF, if there's a little function, little f of x, and our CDF can actually be represented as an integral from minus infinity all the way up to x of this small f of t dt. So if we can write our cumulative distribution function as an integral, then the integrand of that integral is going to be our probability density function. Now, it's not always the case that every single cumulative distribution function has a probability density function. Now, that is something that we will want to save for a more advanced class on probability theory. For us, every CDF is going to have a PDF. So that's one of the finer points. Just know that it's out there, and for a more advanced class on probability theory, that's a topic that can be explored. So for us, all of the cumulative distribution functions that we're going to encounter do have PDFs, and so the fundamental theorem of calculus is going to give us the relationship between the CDF and the PDF. So if we've got capital F of x being the integral from minus infinity up to x of f of t dt, then if we take the derivative of the CDF, we get the PDF. And so what does it really take in order to be a PDF? Well, we need a function that we can integrate, so any integrable, non-negative, real-valued function can be a PDF. So if we can take the integral of it, the function is never going to be 0, we can turn it into a PDF. Okay. So let's kind of recall our axioms of probability that we talked about just a little bit ago. So our probability of any event is going to be between 0 and 1, inclusive. Probability of our sample space is going to be 1, and for mutually exclusive events, the probability that A happens or B happens is going to be the probability of A plus the probability of B. So based on how we defined our CDFs and PDFs, the non-negativity of little f is enough to guarantee that we have axiom 1. If we take the integral of a non-negative function, we're going to get a non-negative value. So we got axiom 1 satisfied. Now, the linear properties of the integral itself, so if we have two disjoint intervals that we're integrating over, well, the integral over two disjoint intervals is going to be the sum of the individual integrals over each portion. And so that is enough to give us what we need for axiom 3. Now for axiom 2, that the probability of our sample space is always going to be 1, and for the non-negativity, and we want our integrals to always be less than or equal to 1, we have to do something called normalizing the integral so that we can obtain axiom 2. Alright, so let's see how that might happen. So what is this process of normalization? So let's just take any old function that we want to have. So we just take little f to be the map from -1 to 1 into the real numbers of f of x is equal to x squared. So if we find the integral of the function over our entire domain, so everything that we have, then we do the integral from -1 to 1 of x squared dx. So that's going to give us 1/3 x cubed from -1 to 1. So we get a value of 2/3 for the area underneath that curve. And so here's where the normalization actually takes place. So we normalize the function little f by taking our integral from -infinity, or in this case from -1 up to x of t squared dt, so the integral of our function, and we divide by the total area underneath the curve. And so if we divide by a, that's going to give us 3/2 the integral from -1 to x of t squared dt. If we take the derivative of that, now we get our original function, but we get it multiplied by a constant that will guarantee that all of our integrals, or all of our probabilities, will have values between 0 and 1. And so that's really what we mean by normalizing the function. You may have seen something similar to that back in maybe a multivariable calculus class, in which you took a vector and you divided by the length of that vector. So you divided a vector by its length and then obtained a unit vector. So you're getting a vector of length 1. In essence, that's kind of what we're doing here. We're normalizing, we're dividing a function by the the length of the function, and so we always get something that's going to give us a value of 1 when we integrate over the entire region. So as an exercise to kind of go along with that, to show that you can use any function that you want, as long as it's non-negative. So let's do the normalization. So find the normalization constant necessary. That's what capital A is. So the normalization constant necessary to form a CDF from our function little f from 0 to 2 pi into the real numbers, such that f of x is equal to sine of x plus 1. Now if you go through this process, you should end up to find that your normalization constant should be 1 over 2 pi. So give that a try, see if you can come up with that answer. Now let's take a look at some of a major difference between the discrete random variable case and the continuous random variable case. Okay. So if we've got two real numbers, a less than b, then from our properties of integration, capital F, so this is our CDF, is going to be -infinity to b of f of t dt, where f of t is going to be our PDF for our distribution. Well, we can write that as the integral from -infinity up to a of f of t dt plus the integral from a up to b of f of t dt. So what is this first integral? Well, this first integral is our CDF at a. And so if we rearrange these things, we move capital F of little a over to the other side, we get capital F of b minus capital F of a is going to be the integral from a to b of f of t dt. That should remind you a lot of the fundamental theorem of calculus, because, hey, that's exactly what it is. Now, from our axioms of probability, kind of plug in those values, what is this first one? Well, it's the probability that capital X, so that's our random variable, is less than or equal to b. This term is the probability that capital X is less than or equal to a, plus, now what happens when we separate those two intervals? What's the probability that a is strictly less than capital X is less than or equal to b? Remember that these two intervals, or these two sets, cannot overlap. So in order to have this be the probability be a sum, we have to have those two sets being mutually exclusive. They have to be disjoint. So if we're including a in one, we cannot include a in the second one. So if we move that probability of capital X less than or equal to a over to the other side, then we're getting this particular expression. So we've got probability of x less than or equal to b minus the probability of capital X less than or equal to a is going to be the probability of a is strictly less than x is less than or equal to b. So if we kind of put those two things together, so now this side is really this side, which means that this side has to be this side. So we get the probability that a is strictly less than x is less than or equal to b is going to be our integral from a up to b of f of t dt. Alright, so now we're going to make a substitution. We're going to say, alright, I'm going to let h be some small positive number, and I'm going to take a to be equal to b minus h. So I'm moving slightly to the left of b. And so what happens when I make that substitution? Well, my probability that b minus h is strictly less than capital X is less than or equal to b is going to be this integral from b minus h up to b of f of t dt. Now, if we then let h go to 0, so what's happening over here on the left? Well, remember, these are intervals. And so we're taking, as h goes to 0, we're taking something that looks like the limit of a collection of sets. Well, okay, what is that really kind of looking like? Well, if we imagine our first set, so this is some value for h over here, as h gets smaller, so if h is going to get a little bit smaller, then b minus h is going to be a little bit closer to b. And if we kind of keep those intervals going, you kind of see what happens. This one is shrinking down to there, this one is shrinking down to there, this one is shrinking down to there. And if we just dot, dot, dot and keep that process going, then what might we actually say is going to be the limit of that set? Well, kind of a naturally intuitive way of thinking about that in this particular case is going to be that the limit as h goes to 0 of this sequence of sets is going to be the intersection of all of those sets. Well, the only element that's going to be in common with every single one of them is our singleton value b. And so if we do the limit as h goes to 0 of the probability of these sets, well, it's going to be the limit as h goes to 0 of these integral. And so what happens on the left, we get the probability that x is equal to a single value is going to be the integral from little b up to little b of f of t dt. So we're taking the integral, and obviously, you know, from Calc 1, that is going to give you a value of 0. And so what happens, the probability that we get one particular value in the continuous case will always be 0. Now that's different, very different, from our discrete case in which we started. So go take a look back at some of the previous videos. In the discrete case, we started with the probability density function. So our values on the sample space, and then we extended that to the values on the power set. So we started with values that were non-zero as PDF values, extended them to values that could be CDFs. Here we're starting with the CDFs, coming back down to the PDFs, and our PDF value at a particular interval at our particular value will always be 0. in the continuous case. So kind of two very big differences between the continuous case and the discrete case. Alright, so now let's look at a couple of experiments in which we have a random variable, and let's see what happens whenever we switch to a different random variable. So we do a change of variables. Let's see what happens in that case. So we've got, say, a physical system where the state of the system is going to be given by the random variable capital X. The system takes on any value in the interval between 1 and 4 inclusive. And the PDF of capital X is given by f of x is equal to 4 over 609 times the quantity x plus 1 cubed. So now let's say that we want to replace our random variable x with a random variable w. And the relationship between x and w is going to be capital W is equal to capital X minus 2. So now we can say, well, what happens? What's going to be the sample space for capital W? And what is the probability density function for capital W? So if little g of W is going to be the PDF for W, how do we find that? Well, we are doing just a change of variables. And so we can say, well, if x is going to be my value, it's going to run from 1 up to 4, then where do my w values run? Well, w is equal to x minus 2, so at 1, I'm going to get minus 1. This is just a linear function, so all the way over to 4, I'm going to get 4 minus 2 is 2. So that's kind of looking at things geometrically. If I look at them algebraically, well, if I've got my x values being between 1 and 4, well, if I look at the inverse function, so x is going to be w plus 2, well, that means that 1 is going to be less than or equal to w plus 2 is less than or equal to 4. So if I solve for w, what happens? Subtract 2 on all the sides, and so I get negative 1 is less than or equal to w is less than or equal to 2, which is exactly what I see in the geometric picture. And so now if I want the probability that capital W is less than or equal to little w, so I'm looking for the cumulative distribution function for capital W, well, that's going to be the probability of what is capital W, what's capital X minus 2 is less than or equal to little w. Well, if I move that 2 to the other side, this is going to be the probability that capital X is going to be less than or equal to little w plus 2. Well, hey, I know the CDF for capital X. That's going to be the integral from 1 up to w plus 2 of 4 over 609 times x plus 1 cubed dx. So if I do that integration, what happens? I use my single variable calculus, do an integration, I end up with this answer of 1 over 609 times w plus 3 to the 4th power minus 16. And so what is my PDF for w? Well, my PDF is going to be the derivative with respect to little w of the CDF of capital W. So if I take the derivative of this, what do I end up with? I end up with 4 over 609 times the quantity w plus 3 to the 3rd power. Alright, so now we've still got the same experiment. We've still got the random variable capital X, but now let's place a third random variable on this space. Let's say that we've got capital Z is equal to 3 times capital X minus 2. Well, we can ask the same question. What's going to be the sample space for capital Z? And what's going to be the probability density function? So what's the PDF of capital Z? And then finally, the last question, what is going to be the probability that capital Z is going to be less than or equal to 7? Let's see if we could find those values. Alright, so once again, we turn to the geometric picture to start out. So we've got Z is equal to 3x minus 2. Well, we know that's just the equation of a line. Equation of a line with a slope of 3, y-intercept of minus 2. So if we've got our x values going between 1 and 4, if we just graph this line, then what happens, we end up with values. So Z is equal to 3x minus 2. So if we find the inverse function, that means capital X is going to be Z plus 2 over 3. And so if x is going to be between 1 and 4, that means that 1 is going to be less than or equal to Z plus 2 over 3 is going to be less than or equal to 4. Well, if we take this inequality, that sandwich inequality, and solve for Z, we end up seeing that Z is going to be between 1 and 10. So what are our values? And so we see, coming back over to our picture, oops, we made a mistake right there. So that for x equal to 1, we should have a Z value of being 1, not negative 1 down there probably. So, oops, we'll chalk that one up to, oops, sorry, my bad. If we look at the probability that capital Z is going to be less than or equal to Z, so again, we're looking at the CDF of capital Z is equal to the CDF of Z. We do the same thing. What is capital Z? It's 3x minus 2. If we apply the inverse function to both sides of that, we see that the probability is of capital X less than or equal to Z plus 2 over 3. Well, we know the CDF of capital X. That's going to be 4 over 609 times 1 up to Z plus 2 over 3 of x plus 1 quantity cubed dx. Well, if we do the integral, so we're able to do the integral on that, and here's our answer. Well, if we want the probability that capital Z is going to be less than or equal to 7, we take this value, we take this expression, we plug in 7 for little z, and what do we end up with? Well, the probability that Z is going to be less than or equal to 7 is going to be 240 over 609. And once again, if we want the PDF of Z, capital Z, we're taking the derivative with respect to Z of our CDF, and that, so it's just going to be the derivative of this function, which is going to end up just giving us 4 over 1827 times the quantity 1/3 Z plus 5/3 to the third power. Alright, so after those two examples, you might be thinking, well, you know, isn't there a shortcut for us if we're doing a change of variables? What would be the shortcut? And is it always necessary for us to go through the CDF and then take the derivative to get back down to what the new PDF is going to be? Well, can't we just make things a little bit shorter? Well, the answer is yes, we can. And here's the theorem that's actually going to tell us how we go about doing this. And so we're going to start with a continuous random variable x that has a PDF little f. We let A be the one-dimensional space where, so we're going to let A be the set where little f is going to be strictly positive. Then for our new random variable y, for this particular transformation, U is going to define a one-to-one transformation on this set from A into the set B. So B is just going to be the image under U of A. And we're going to suppose that this inverse function is continuous, and that the derivative of the inverse is going to be non-zero. So here dx dy, we've actually got this written as y as a function of x. So dx dy is going to be the derivative of the inverse function. Okay, so we want that derivative to be non-zero on that image. And so the PDF of y, so the PDF of our new random variable, is going to be f evaluated at the inverse function for y at y, and then times the absolute value of the derivative of the inverse function. Okay, and so let's see if we can figure out, well, let's see if we can go about and prove why this is going to be true. Alright, so suppose that our inverse function, u inverse of y, is increasing. So if u inverse is increasing, then the derivative dx dy is going to be positive, and so we take the absolute value, that's going to just not change anything, and we just get dx dy. And so here's where we need the increasing part. So we have the probability, so the CDF is going to be y less than or equal to little y. Well, now we're going to apply that inverse function. And if we're applying that inverse function to this particular interval, we end up with a new interval, but the direction of the inequality stays the same. And so here's where we're going to break our argument up into an increasing function or a decreasing function. Okay. So if our inverse is increasing, then the direction of the inequality stays the same, and so when we apply the inverse function, we get the probability that capital X is less than or equal to u inverse of y. So remember, this step should look familiar as a generalization to what we did in those two previous examples. And so we know what the CDF of capital X is. It's going to be minus infinity up to u inverse of y, f of x dx. Alright, well, let's turn to the fundamental theorem of calculus. And so what we have in that case is really a function of a function. So go back to your fundamental theorem, your Calc 1 days, and you're seeing that the outside function is the integral itself, the inside function is the inverse function that we have as the upper limit. And so the chain rule is basically going to give us the answer. The chain rule coupled with the fundamental theorem of calculus. So if we take the derivative of this, we get the derivative of the outside function. Derivative of the outside function is the integrand. That's our fundamental theorem of calculus. So the derivative of the outside function, keep the inside function the same. So f of u inverse of y times the derivative of the inside function. Well, the derivative of the inside function is the derivative of the inverse, and so we get our values. If we look at the case in which our inverse function is decreasing, then our absolute value becomes the negative dx dy. But what would happen in this step, when we apply the inverse function, our inequality would change directions. When our inequality would change directions, now what's going to happen is that's going to introduce a negative. That negative is going to get filtered through everything, and so I'll leave that as a little bit of an exercise for you to work through on your own, but it'll still end up giving us the desired conclusion. So hope you've enjoyed this next little segment on CDFs, PDFs, and random variables. See you all next time.